Welcome to my series of AI. In the RAG, we saw these concepts called vector DB, so on and so forth. Okay, so we'll dive deep into it. There are these concepts called word embeddings, cosine similarity. Okay, so we'll see what those are. Okay, so what is an embedding? Okay, so an embedding vector just converts a word into numbers. Okay, so as we know, the machine understands everything as numbers, right? So it doesn't understand a word, so it will understand a word as a number. Okay, and it's not just a single number, but it's a list of numbers. Okay, so for this particular example, we'll just make that vector a list of numbers so that we can represent it uh, visually on a two-dimensional plane. Okay, so let's say our vocabulary is only of 10 words. Okay, and I'll represent it in a two-dimensional vector like this. King is 0.9 comma 0.8, right, so on and so forth. Okay, uh, now this way what will happen is that words that are similar, they will have vectors which come close together. Okay, so let's see how that happens. So I'll plot it on this two-dimensional plane. You can see king and queen are similar, right? They're humans and they're royal, right? So they come together. Man and woman, they're humans, so they come close together. Okay, apple and orange are fruits, they come close together. Okay, so that's how this word embedding and the intuition behind capturing semantic or meaning in words in these vectors works. Okay, now the other concept like cosine similarity, right? Now cosine similarity has a very simple formula, which is a dot product of two vectors a and b divided by multiplication of mod of these two vectors. Okay, now dot product, as you know, is basically if the angle between these two vectors a and b is theta, right? This is ab cos theta divided by ab, right? It would be cos theta. So say for example, this example of king and queen, right? Now as you can see, the theta, the angle between them is just 0.21 degree, right, which is close to 0. So the cos theta is very close to 1. So the cosine similarity is very close to 0.999, which is very close to 1. So they are highly similar. Okay, so that's how this uh, vector representation of words and the cosine similarity for similarity measure works. Okay, now what I'll do is I'll kind of uh, plot these clusters, right, which is the words which uh, kind of related to royalty, right? Like king, queen, they form a cluster. Words which are related to humans, right? They form a cluster. Fruits, right? Vehicles, animals, so on and so forth, right? So as you can see, these words that have similar meaning come together. Okay, they will have like this cosine similarity of a very high value, very close to 1. Okay, uh, now how does semantic search work, right? So let's say there is a query of royal female, right? So it will represent that as like a vector, right? And then it will do a measurement of all these words, right? And then it will basically say queen is the closest, right? Apple is the farthest. Okay, and it will give the result as queen from our vocabulary, right? Or from our corpus of 10 words, right? Queen will be closest to this query of royal female. Okay, that's how a semantic search would look like, right? So you already have a vector representation of all your words, right? All the corpus or the members in your corpus. Similarly, you give a vector to the query that comes in and you find whatever entity in your corpus is closest to that query in terms of the cosine similarity, right? That's how the semantic search would look. Okay. Now, the earlier representation of words was much simpler, I would say, right? So the cosine similarity has a little sort of a twist to it where it doesn't consider the magnitude of the vector, right? Because it divides by the magnitude of the vector, right? So it just looks at the angle between these two entities, right? And that's what we are trying to capture here, right? So say, for example, uh, there is a difference between a man and a king, okay, but they are kind of, in the same direction, right? Now, the difference between man and king would be only the that of magnitude, and that magnitude would be like a royalty drift, right? As we would call it. Like, so king is more royal. Okay, so interestingly, this is sort of what you'll see where king minus man, like a dimension or the difference in magnitude of these two vectors would be kind of very close to the uh, difference of magnitude between these two vectors of queen and woman. Okay, so that is like a drift in magnitude. Okay, which is kind of interesting in cosine similarity for different words. Okay, uh, now as I was saying, right, these are not just magic words, right? So these vector values are actually learned from training data, right? So how does it work? It's a very simple example of a very popular training algorithm for learning these vector values called word to vec, right? So it basically takes a word like a king, right? And it runs this embedding algorithm uh, through a neural network, right? In the context of the training data that you have got, right? So it kind of, says that, oh, king appears in context of throne, so on and so forth, right? And it will adjust the vector values accordingly, right? And outcome these vector values. Now, one interesting concept here is like, it's learned in the context of training data, right? So say, for example, if there was a word like apple, right? And if the training data comprise only of computer companies data, right? Then Apple would mean like a computer company called Apple, right? Otherwise, it would probably mean a fruit apple, okay? So that's an interesting learning part of these vector values, okay? Now you would say that, oh, like, this is very toy example, right? 10 words, like 2 dimensions. Tell me more, okay? Now, uh, conceptually, it's still the case, right? But dimensionality wise, this word to vec, for example, the algorithm that we saw earlier, it has 100 to 300 dimensions. So it's not very easy to represent these words like what we drew on a two-dimensional plane, but it will be like a hyperspace of 200 dimensions if there were to be 200 dimensions for these vectors, right? But another algorithm, it's much higher, it's 768 dimensions, right? Now all these LLMs, right, GPT-4 class, they have 1000 plus dimensions, right? uh, but mind you, higher dimension means more expressiveness, but it is more complex, right? It's more compute, more network, more cost, right? And beyond certain threshold, right, which is kind of found to be like 384 to 768, right? The returns are diminishing, right? So actually, LLM like GPT-4 class are really stretching it. Okay, so that's the scoop on this word embedding and cosine similarity and how it works in the RAG for the similarity or the semantic search as we know it. If you like the video, click the like button, subscribe to the channel, and good luck exploring RAG, AI, and whatever journey you are set on.